In this video, we give you some technical background on how you can boost image information content with TRUESHARP deconvolution. In general, with those kind of imaging or image processing problems, we're facing two challenges, and those are noise and background. And we better deal with both of them for optimal results. So let's start with noise. In a simplified way, or a simplified manner, you can picture deconvolution a bit like curve fitting. So you know this, we have noisy data, those are noisy measurements, and curve fitting means we ask a computer to, let's say, put a line through there in an optimal way. What does optimal mean? We simply ask an algorithm to move and tilt this line until the distances here between the data points and our curve become minimal. And deconvolution is very similar. We have noisy data, so those are your intensity measurements, the different pixel positions. And one difference is that it's not a line. Line would be a boring sample. So we have to ask the computer to plot some curve through it that goes through all the data points, or comes as close to the data points as possible. Now what the computer does, without any further assumptions, it usually comes up with something like this, because this goes perfectly through all the data points. But it's obviously not what we want. Although you all know those images, so as you can see here, this is the typical Richardson-Lucy deconvolution with those wave-like artifacts that in the image show up as two-dimensional water waves. One solution to this has been known for many years. It's called regularization. And regularization simply means that we give the computer some slack with these distances. So we say, look, maybe don't make the curve go exactly through all the data points. Try to come close, but at the same time, make this curve reasonably smooth. And that's the problem there. I mean, the images look good, but the problem is what means reasonably smooth. Doing this means we're using assumptions, or we're making assumptions about the sample, namely that it's smooth or that it's sparse. So we assume certain qualities that a sample has, and it's good and well if the sample is smooth or sparse, but it might not be. And from the processed images, you never know. So regularization tends to produce artifacts, so it tends to produce structures in the processed image that weren't really there in the original sample. And again, most of you may know these spider web artifacts that we see here, that are a typical result of regularization. So with TRUESHARP, we do things differently. We don't make any assumptions about the sample, really. We use one physical fact, a very simple fact, namely that noise is random. So while performing deconvolution, we look at parts of the signal that change randomly between iterations. Those signals we know are noise, and we know that the rest is structure, is our true object. So this way we can separate noise from the object, and we can produce nicely deconvolved images without any artifacts and no water waves, no spider webs in between, simply by using the fact that noise is random. And that's the whole trick. There are no assumptions in there about the sample. So this way, we can put a check mark here next to noise, and what remains is background. So let's look at what we do to deal with background. So in this image, we got rid of noise without producing artifacts, but you can see there's still a lot of background in it. First, let's look at traditional deconvolution algorithm. So this is a deconvolution, black box. It's not important what goes on inside. We give it a measured image. And of course, a point spread function, PSF. Now it's important to realize that the measured image contains both signal and background. And it's one thing, it's the same image. They're not discernible, they're completely mixed up in there. So the result is that the deconvolution algorithm, a standard deconvolution algorithm, cannot distinguish between signal and background. So it will produce an image of the object that's supposed to be in the sample, including background. So the background is in here, mixed up with the signal, so it also shows up in the final result. Again, TrueSharp does things differently. With TrueSharp, again, let's just take a black box algorithm here. We give it, of course, PSF and signal and background separately. This way, TrueSharp is able to recover the true object that's present in the sample without the background. Now, of course, you ask yourself, what can we give it? How can we give it signal and background separately? After all, they're in one single measured image, and they're separate ways, different ways on how to separate the background from the measured image. One is simply we use some kind of estimation algorithm. So there are computer programs which can recover, estimate the background given a measured image. Obviously, it's much more favorable to physically measure the background instead of estimating it. And one way of doing this is time bow. Prime example is your sample has autofluorescence. Autofluorescence has a different lifetime than the fluorophores, so you can easily separate the signal from the autofluorescent background using lifetime imaging. But this might not always be the case. What you can do in any sample, though, is use a matrix ray detection. This is another way to physically measure the amount of background in the sample without depending on the lifetime. If we do stat imaging, we can do one more step. Then we can use time bow lifetime imaging to get a better fix on the PSF. And that's because the stat donut modulates the lifetime of the fluorescent molecules. And since the stat donut varies locally, we have spatial information encoded in the lifetime. And we can use this to sharpen the PSF and to boost the resolution further using TrueSharp recovery. And of course, we can do all this together. We can use matrix to get rid of background, physically measure background and remove it. We can use time bow, sharpen PSF, and boost resolution even further. There are several packages on the market. There are software packages for estimating background. There's, of course, array detection, lifetime imaging. Abberior is the only company where you get all that in one single package. So with this, we can put a check mark on the background, and this is the result. You can see we got rid of noise, no artifacts, got rid of background, and produce nice, sharp, clean images of nuclear pores here. If you want to know more about the benefits for your application, how this works on different images, we have a second video, so check it out.